Hi there, my name is Philip D and I work in the Faculty of Health's Academic Development Department, or the ADD, previously known as the PDD, the Personal Development Department. And this is the third instalment in a series of 5 videos covering key concepts of quantitative systematic reviews. So the story so far. Back in video 1, I covered in broad terms what a systematic review is, why we should carry one out, and the main components that make up a systematic review as piece of research, thinking in particular about you doing this as the final component of your MSc. In video 2, we took a deep dive into an actual published systematic review, and this allowed you to see what a write-up of a systematic review might look like. Although as we were looking at a published paper, that particular example was much shorter in length to what you will produce. Now here in video 3, we are going to remind ourselves of the key statistics that you will come across in your reading of the primary research papers. I will here also be introducing you to hazard ratio, odds ratio and risk ratio, but then we'll illustrate them further in video 4. I will also leave to the next video, video 4, to explain in context other key statistics that are particularly specific to doing a meta-analysis within a quantitative systematic review. And finally, in the very last video, video 5, I will show you how to actually carry out a meta-analysis using the freely available program RevMan. Okay, so let's crack on. First off, in this video, we are going to look at how data is typically summarized in research papers using charts and tables. We need to try not to be fazed by these, and so the key point here from your perspective is to be patient and to consider carefully what the researchers are telling us. This will lead us on to what are the more common descriptive statistics, and by this I mean those values that are going to be relevant to you when you are ready to extract data values ahead of pooling, i.e. combining them across several research papers in order to carry out your meta-analysis. But that last part will have a video all of its own. The bridge between descriptive statistics, a summary of their data, to inferential statistics, where they hopefully draw some conclusions, is via the concept of confidence intervals. These are simply a statement of the precision of their results. Confidence intervals are also used to inform us of statistical significance and complement the use of p-values, also for the same purpose. The last part will be an exploration of some less familiar descriptive statistics that you are still likely to come across in your research reading. For example, with diagnostic tests and with risk factors affecting disease outcomes. Okay, I've said a lot so far without explaining anything in detail yet, so let's dive in. Let's first think about how data is presented in research papers. Now, much of this should be pretty familiar to you from your school days, but if you, like me, your school days were many years ago, then I'm prepared to acknowledge that we might be a bit rusty and need a bit of gentle reminding. But first, and before I get into all this, I do need to remind you, in case you didn't know, that not all quantitative data is of equal quality, as it were. There is a recognized hierarchy of data types. At the bottom, the least sophisticated types of measure are what is known as nominal level data, or nominal variables, also sometimes referred to as categorical variables. These are when you have different groups, such as gender or hair color, or simply grouping allocation in an experiment. You cannot attach an obvious number to describe these nominal values, but you typically would give counts, otherwise known as frequencies, for the occupancy in each group. Of course, statisticians, for convenience, may code these grouping variables using number labels. For example, they might code male equals 1 and female equals 2. But it is important to recognize that these number labels have no intrinsic value in themselves. Frequencies, on the other hand, are a valid measure. Next up, we have ordinal level variables, and this is where we can only rank the data. If you've ever filled in a questionnaire and had to tick a box for a question that asks you if you strongly disagree, felt neutrally, agree or strongly agree, you know, that kind of thing, then you were dealing with an ordinal, i.e. a ranking variable. Again, there is likely to be no natural number associated with each level or possible grouping of the variable, but when a statistician codes or labels the groups, they do so typically with ranking numbers such as 1, 2, 3, etc. The top two, interval and ratio level variables, are measures that we would all recognize as such. They are things like weight and temperature. Many textbooks do not even bother to distinguish between them and call them collectively scale variables. But for the record, interval level variables can sometimes go negative, at least in theory, e.g. degrees centigrade or height above sea level. And this is because they are using a measuring scale that has set a zero that may seem somewhat arbitrary in that it could have been set elsewhere. So degrees centigrade, for example, have zero set at the temperature when water freezes, and height above sea level is a way of measuring land, e.g. mountains, with respect to the body of water known as the sea. Finally, ratio level variables do have an absolute zero. In the case of temperature, this would be degrees Kelvin. Other examples of ratio level variables are weight, length, and time duration. So here I'm leaving you with some examples as a summary. Okay, on now with how quantitative data is represented in research papers. Let's start with bar charts. These are used mainly for nominal level variables, remember, also known as categorical variables. In this picture here, as well as the bars representing the frequency, the count for each group, they have also shown the measure of spread for each group, known as the standard deviation. But we'll say more about that later. Next is histograms, and at first sight they do look a lot like bar charts, but there is an important difference. These are used when the variable is higher than ordinal and specifically for what is known as continuous data, which by the way explains why there are no gaps now between the bars. All values have to be accounted for. So continuous data, to put it simply means measured values that could have decimals. They are usually interval or ratio level measures. In the example here, the histogram has also a curve fitted onto it so the researcher and therefore reader can visually appraise if a normal distribution curve is a good fit. Of course, you've all seen pie charts, and these can be used to visualize nominal level data, for example groups, and they're also sometimes used to visualize higher level variables such as ordinal, interval and ratio. But we all know that in the great majority of research papers, most data is expressed either within open text or within tables. So let's have a brief look at an example which will be a nice segue into some basic descriptive statistics. So here is a paper I found from 2020, which is a systematic review and meta-analysis considering the effects on mortality due to delay in treatments across a range of cancers. So here is their abstract, which ends with the predictable, perhaps, conclusion that cancer treatment delay is a problem worldwide, and even a delay as small as 4 weeks has a measurable increase in mortality across a range of cancers. Of course, what we are interested in here are the statistics as reported in such papers as this. First, some easy numbers to understand. This review used 34 studies with a total sample size of over 1 million patients. So far, so good. Next, they give a p-value, which is a guide to helping us conclude whether the differences they saw could have been due to chance or not. But more about p-values later. And finally, we are presented with a series of measures of risk. For example, here they quote something called the hazard ratio. In addition, they also quote a confidence interval. Again, we will address these a little later on. So already we have a mixed bag of both familiar and unfamiliar concepts. Okay, so these concepts will be dealt with in more detail through the course of this recording, but I hope you can already see that it is important to try to understand what this all means. Otherwise, we are compromised in our ability to evaluate a piece of research, which is a crucial component of any systematic review. The other thing I will show from this paper, and I fully acknowledge it is where for a lot of us our eyes just glaze over, is a table of results. This is where data is more commonly summarized in research papers, and you must train yourself to not just skip over them. In this case, this table is the extracted results from various primary research papers prior to a meta-analysis, but you will come across all kinds of tabulated values. What you must learn to do is to focus. Which bits can you initially gloss over, and which bits do you need to concentrate on? In this particular table, we should be drawn to the fifth column, which is where the key data lies. Now, this is real-world data that we are looking at, and this paper has not conveniently provided data in exactly the same format. For example, although the column heading is that the data given is the median age, several of the entries are actually mean ages. As a measure of spread, there is a mixture of the range, the interquartile range, and the standard deviation. So for these authors, they had to think very carefully as to whether this was going to prevent them from carrying out a subsequent meta-analysis. For your part, as a reader of such research, you too should be thinking about the quality of data as well as simply what the values are. So what I'm saying is, tables are nothing to fear, but you do need to be patient when studying them and try to home in on the part that is of most relevance to you and your particular research question. And then, of course, try to understand what you are looking at. Which brings us nicely onto a broad review of key statistics that you will come across and ideally need to have an idea of what they mean. So let's take a deep breath and take a big step back. And start by considering descriptive statistics, which simply means giving summary values of the group's data that we have measured for various variables. There are always two summary values used to summarize each group characteristic for a given data set, and these are the average and the spread. Let's start by reminding ourselves what the average is. As you should remember from your school days, there are three common measures of the average: the mean, the median, and the mode. The mean value of a dataset is where we add them all up to get a total, then divide this total by the number of values in the dataset. The median is where we arrange the data values in ascending order, then we pick out the middle value, and that is the median. It would still work the other way around, i.e. in descending order, but I'm going here with the more common approach. Finally, the mode, which is simply the most common value of the dataset. Note that, just to confuse you, in textbooks on statistics, you will also see the average sometimes referred to as the central tendency or even as the location. So let's try this out with a very small dataset. I'd like you to pause the recording for a few moments and see if you can identify or calculate all three common averages, the mean, the median and the mode, for this dataset, which is comprised of just 7 values. I've made it easy for you by already arranging them in ascending order, and there should be no need for pen and paper. Okay, so how did you do? The answers are 3 for the mean, as the total was 21, and you then divided by 7. 2 for the median, which was the middle number, which you will have found was the very first 2 we can see after that initial row of 1s. And 1 for the mode, as there are 3 of them and only 2 of the 2s. Now, without the reminders I've just given about the different types of average, the great majority of students would have said off the cuff that the average for this dataset is 3. And it is important to realise that we, and therefore researchers, need to be precise when talking about statistics. The word average, as we have just seen, is too imprecise. Of course, it all gets a bit more involved than this simple example might suggest. For instance, the mean may not even be a value in the data set. For example, it can be a decimal. Think of the well-known statistic that the average family has 2.5 children. Also, what happens to the median when there are two middle values? Well, then we'd simply split the difference, i.e. we take the mean of those two middle values. And finally, of course, it is possible to have more than one mode. Now, there is a whole video that I previously made regarding the average, and if you're really excited about this, I will put a link in the resources slide at the end. Now that we have reminded ourselves about the different types of average and about the hierarchy of data types, we can now say something about when we should use which type of average. For nominal level data, there is only one choice for the measure of average, and that is the mode. For ordinal, i.e. ranked data, then we should be using the median. Of course, we are still at liberty to use the mode, and this might be done if we are also visualizing the data using a bar chart. Finally, if our data is of the highest level, namely interval or ratio, then we would typically use the mean. But again, we can, if we wish, use lower measures of average. Now, there's a bit more to it than what I've just said. For example, if a questionnaire is composed of many ordinal items using Likert type questions, all measuring different aspects of the same thing, and so the recorded score is an overall total, for example in the Maslach burnout scale, then there is an argument to say that we could use the mean rather than the median for our measure of average, because now we have a much wider range of possible total scores, and these are starting to look like continuous data and therefore interval or ratio. Another complication is if our data is skewed in some way, i.e. is not symmetrical. Well then, using the mean, even for interval or ratio level data, will not give a good representative value of the data set. A good example might be the wages in a large factory. These are skewed towards a small number of managers and the owner whose salary is way higher than the great majority of workers. In such cases, the median would be a better measure of the typical value for the group. The separate video on the average that I give at the end will explore this also a little further. Now moving away from the average and onto the second summary value that we need to describe the overall feature of a collection of data, and this is the spread. As with the measure of average, there are three common ways of measuring the spread of data. And these are the range, the interquartile range, and the standard deviation. And I'm willing to bet that you have at least heard of the range and the standard deviation from your school or college days. Again, I'm not going to go into great detail because I have also made a separate video on this, but you should recall that the range is simply the biggest value in the dataset minus the smallest value. The interquartile range uses the same starting technique used to find the median. All the values are laid out in order, but then the dataset is split into two. We next find the median of the lower half and call this value the lower quartile. Then we find the median of the upper half of the data and call this value the upper quartile. And finally calculate the upper quartile minus the lower quartile to give us the interquartile range. And you'll notice that for both range and interquartile range, we are ultimately using only two numbers. Finally, and the most sophisticated measure of spread, is the standard deviation. This is a bit like the mean in that each value in the dataset is used to calculate its value. If you want to dive deeper, I advise that you check out my other video on this. Again, in textbooks on statistics, just to confuse you, you will also see the spread, sometimes referred to as dispersion. Okay, like the choice of which average to use with different variable types, we now need to think about which measure of spread should we use with nominal, ordinal, interval or ratio level data. First off, if your data is nominal, i.e. categorical, then even though there is a measure of average, the mode, there is no measure of spread that goes with this. This is perhaps obvious when you realize that for nominal level data, there is no unique way of ordering these categories. Next, if your data is ordinal, i.e. ranked, then you should expect to be using the interquartile range. And finally, for interval or ratio level data, we would expect the measure of spread to be the standard deviation. Notice that the measure of simple range is not recommended anywhere here because as it uses the extreme values, i.e. the smallest and the biggest, it is therefore sensitive to outliers, meaning the presence of any untypically big or small values, which would make the group spread seem far wider than it generally is with most of the data values. And so using the range might give a misleading representative value for the spread of values for the whole group. Again, we might have to modify these decisions if the data was skewed, and again, this is covered in the additional video on the spread that I give at the end. So we are now in a position to understand one final way of visualizing data that may you come across in papers, and you will likely have seen this in your maths lessons back in school. And this is of course box and whisker plots, or as I learnt them, just box plots. They are also sometimes called 5-point summaries or 5-number summaries for reasons that will quickly become clear. Okay, you will either see box and whisker plots like this, which can be presented standing vertically, like this one here, or it might be drawn on its side horizontally. They both mean the same thing either way. Now recall my comments about the median, which was one of the measures of average. Well, the median is represented here by the line going across inside the box. Notice it does not have to cross the box exactly halfway because the data may not be symmetrically distributed. In fact, that is one reason why looking at the box plot is useful. It indicates whether the data is likely to be normally distributed, i.e. symmetric. Also, if you think back to what I said about the measure of spread, which goes with the median, i.e. the interquartile range, well, the lower quartile here is labelled as the first quartile, and the upper quartile is here labelled as the third quartile. In other words, the interquartile range is simply the length of this box. The two whiskers on either end of the box are reaching out to the maximum value here at the top and the minimum value at the bottom. Sometimes you won't see these flat ends to the whiskers, but instead the whisker line will just stop. Also, very occasionally, you will see one or two dots appearing beyond the ends of the whiskers. These indicate any likely outliers in the data, and it will depend on the software being used as to how they are worked out. But a common convention is that any data points that are more than 1.5 times the interquartile range, either beyond the upper quartile or, looking at very small values, 1.5 times beyond the lower quartile, then these are generally regarded as potential outliers. As you see, there are therefore 5 key values labelled on a typical box and whisker plot, excluding any outliers, which explains why it is called a 5-number summary. In addition, in the picture I took here from Google, they have also given the X, which is the mean, and this is typically not included in a box and whisker plot. Okay, a change of focus now. Now I haven't finished with my intended set of descriptive statistics that I want to discuss, but before I do any more, I next need to talk about confidence intervals. And before that, I want to jump ahead and talk about statistical significance. I'm doing it this way around because confidence intervals bridge the gap, so to speak, between plain old descriptive statistics, summarizing what you've measured, and inferential statistics, drawing conclusions from it. Also, confidence intervals will be important in my last set of descriptive statistics that I need to cover. So rather than split my discussion of confidence intervals into 2 time points, I'm going to look at it in full when I come to it. But first off, let's talk about significance, or as it should be more correctly called, statistical significance. So the heart of the idea behind quantitative research is to start with a null hypothesis, e.g., is this couple going to get married? Now, if they say yes, then we can reject the null hypothesis and accept the alternative hypothesis, i.e. they live happily ever after. possibly. In the parlance of nursing or medicine in general, the null hypothesis means there is no expected difference or no effect when we use this new drug or therapy compared to the old drug, for example. And then, through careful design and analysis, the researcher hopes to reject this null hypothesis. But it has to be done in good faith. If there truly is no underlying effect of whatever procedure we are investigating, then the analysis must show that too. So the two outcomes from the statistician's point of view are either to reject the null hypothesis or fail to reject the null hypothesis. Which brings us nicely onto p-values. Any inferential statistical test, for example, a chi-square test, a t-test, an ANOVA test, Mann-Whitney test, etc., and yes, there are a lot of them, they will generate, amongst other things, a numerical value called a p-value. In simplistic terms, this is a probability, so its value can only lie between 0 and 1, as it is typically expressed as a decimal and not in this case as a percentage. This probability gives the likelihood that the difference seen in the measurements could have arisen by chance alone. It actually means something a little bit more involved than this, but this pseudo definition, if you will, is good enough for our purpose. So, there is a common convention you are very likely to have already come across, and that is if the calculated p-value resulted from using the relevant inferential test comes out to be less than 0.05, i.e. less than 5% if we were talking at percentages, then we can reject the null hypothesis and so accept the alternate hypothesis. In other words, it gives evidence to support our claim that one drug is better than another drug, for example. Now, there's two things further need to be said here. The first point, this number has not been plucked out from the air. There is a mathematical basis for this, and this, along with the discussion about confidence intervals and statistical significance in general, is covered in more detail in my significance video, which I give a link to at the end. The second point is that this is not a universal rule, only the most commonly adopted rule. For very expensive or potentially damaging interventions, such as a chemotherapy drug or a COVID vaccine, then researchers might demand to attain a p-value of much less than 0.5, say 0.01, before they are willing to claim statistical significance and proceed with licensing the new drug. Okay, the last topic of descriptive statistics that I want to touch on is the idea of a confidence interval. This is also a bridging concept to inferential statistics, where we make inferences, i.e. conclusions about the results of the research. That will be where statistical significance and p-values actually enter the picture. Now, as I have already mentioned, I made a whole separate video on confidence intervals, statistical significance and p-values, so I will only give the highlights here and direct you to the full discussion video at the end. So, what does a confidence interval actually look like in reported research, and how should we interpret it? The confidence interval is often given alongside the measure of the mean in research papers and may look like this. The number on the outside of the brackets, in this case the value 20, is the mean of their group of values, and there will typically be two or more of these measures, one for each group. Now, the mean, of course, is a measure of average that has taken into account each of the values in the group of data and could be seen as their measured value. The two numbers inside the brackets, the lower and upper values for the confidence interval, are calculated values and use the value of the standard deviation, i.e. the spread, as well as the group size in the calculation of this. What is crucial to understand is that each measure carried out in a piece of research, e.g. the group mean, is essentially an estimate of the population value. In a real piece of research, we only have a sample of this population to work with, but we hope that our measured values of the average, etc., are not far off the true value that we would get if we had access to absolutely everyone in the particular population of interest. The role of the 95% confidence interval then is to say we are 95% confident that the true value, i.e. the population value, lies somewhere within this range, It can therefore be seen as a plausibility range of values in which the actual population value, also known as the population parameter, is likely to lie. I like to think of this interval as some kind of measure of precision for the mean. As the sample size increases, this interval shrinks and becomes narrower, i.e. the measured mean becomes more precise as a measure of the population. Another nice way of showing confidence intervals, which I've shown here, is by using a number line, which you'll be familiar from schools. So here the dot in the center is our measured value of the mean derived from the data, and the two bars to the left and two to the right show the extent of this plausibility range. Now, it is quite rare that they show the confidence interval in this way, either in textbooks or in research papers, but I think it's a nice way of thinking about how confidence intervals are just a spread of possible values that the true value could be. Okay, so we see that confidence intervals can be seen as a measure of precision for population parameter, but how do confidence intervals link to statistical significance? Well, imagine we have, say, two groups, and are expecting or hoping for a difference between them because of some new drug or therapy that we have administered to one of the groups but not to the other. So we expect, or rather hope, that the difference between them in terms of outcome is not zero, so that we could then claim some kind of success. Now, many researchers give the size of the measured difference as a single value, i.e. their difference in the mean. And they also give the associated 95% confidence interval for this measured difference. So whatever value is given for this difference, and therefore assume in general that this measured value is not zero, we then look to see if zero is included in the range of plausible values, i.e. if the 95% confidence interval includes that value zero. If not, then we could claim statistical significance, but if it does include zero, then we cannot claim statistical significance. The actual difference seen could very well have been due to chance alone. In this first example, that is exactly what we see. The difference measured was 3, but the 95% confidence interval of plausible population values included the value 0 of no difference to be a plausible true value. So in this first example, we cannot declare statistical significance, or, to use the parlance of research, there is insufficient evidence to reject the null hypothesis. On the other hand, if the 95% confidence interval does not include 0, then we can say that the results were unlikely to be due to the play of chance alone, and therefore that the results are statistically significant. And this is shown in this second example. You'll see that again the measured difference is still 3, but now the range of plausible values given by the confidence interval does not include the value 0. Zero difference is therefore not a plausibly true value for the population from which this sample has been drawn. For this second example, we can reject the null hypothesis and can claim statistical significance. The obvious difference visually between these two examples is that the second example, the one on the right, has a narrower confidence interval, i.e. a higher level of precision, and this was almost certainly due to a larger sample size. Now, the important outcome isn't necessarily this better precision, but that the value 0 did not appear as a candidate value for the true population parameter. So now might be a good time to have a break before we go on to the second half of this presentation. So go get a cup of tea or make a note of the time point for this bit if you are coming back later. So welcome back if you went and lie down in a dark room for a bit. And this is where the concepts get a lot less familiar. It is highly likely in your research reading that you will come across descriptive statistics associated with diagnostic testing or with the chances of developing a disease associated with a possible risk factor, such as smoking or a high-fat diet or the taking of hormone replacement therapy, etc. In such cases, there is a confusing array of measures that you will see, so I will focus only on those that I have seen reported in systematic reviews. So let's start with two common measures that come out of diagnostic testing, such as screening procedures, also known as a screening tool for breast cancer. Crucially, we have collected data and we have tabulated in what is grandly called a contingency table. And the simplest such table that we could have is a 2x2 table. Let me show you what I mean. In any diagnostic test that we are interested in, we are interested in the presence or absence of a particular disease, for example, breast cancer. Now we run the screening test on a whole group of volunteer participants, and we arrive at a table of frequency values, i.e. counts, with 4 possible entries. Those who are true positive, i.e. they tested as positive for the cancer and they really do have the cancer. Then there are the false positives, those who also tested positive, but it later turned out did not have breast cancer. Similarly, we have true negative, those who tested negative and indeed really did not have the cancer. And finally, false negatives, those who have also tested negative but really do have the breast cancer. Now consider the consequences of participants occupying each of these 4 categories. A true positive is upsetting, but now that they can move you on to treatment. A false positive is also upsetting that you thought for a while that you had the cancer, but were then told on further investigation that this isn't so. Now we clearly want a minimum number of people in this category, 0 if at all possible, because we are causing undue anxiety with this outcome to our diagnostic tool. Thirdly, for the true negative, they are genuinely without the disease and they are given the all clear and are therefore good to go. And finally, we have the false negatives. Now this really is problematic because the participant has been told that they have been given the all clear in error. They really do have the cancer, but they are not yet being guided on to treatment because it was missed at this screening stage. This is the worst category to be in. Your cancer diagnosis has been delayed and this can only worsen the prognosis. And therefore I hope you will agree that a false negative is indeed worse than a false positive, and therefore reducing the number of false negatives to an absolute minimum in any diagnostic tool must be a priority. So the ideal scenario, which by the way is almost never achieved, is where we have 0 counts in the false positives and 0 counts in the false negatives, and all patients are given their correct diagnosis from the screening tool. In reality, of course, a more realistic ideal to aim for would be to only have very small numbers in the false positives and false negative categories. Now there are 4 measures that can be extracted from just these 4 tabulated values. Each is a different measure of validity, i.e. the truthfulness or usefulness, if you will, of the diagnostic tool. And these measures are sensitivity, specificity, positive predictive value or PPV, and the negative predictive value or NPV. Each of these has its own interpretation or perspective of validity. These first 2, the sensitivity and the specificity, are the more commonly reported in research, and this is because they are measures from the perspective of the tool itself, i.e. how well is a diagnostic tool performing generally. The last 2, the PPV and the NPV, are less well reported because, as we shall see, they are values of greater interest as a perspective from the individual patient's point of view, who is the one receiving their particular diagnosis. But for my money, that makes them just as important, if not more so. Starting with the sensitivity, this is a measure of the ability of the diagnostic tool to correctly identify someone who actually has the disease. This can be expressed as the probability that someone with the disease will indeed test positive. We want this value to be as close as possible to 1.0 or 100% if you'd rather work with percentages for the probability. The specificity, on the other hand, is the ability of the diagnostic tool to correctly identify that someone without the disease will indeed test negative. Again, expressed as a probability, it is the probability that someone without the disease will indeed test negative. And again, we want this to be as close to 1.0 or 100% if you will, using percentages. So a good diagnostic tool is one that has both high sensitivity and high specificity. Moving on to the final two measures of validity. Firstly, the positive predictive value, or PPV. Now, this is a statement of the probability that someone who has tested positive really has the disease. And note, this is not the same as the sensitivity, as we shall see in a moment when we consider an actual example. And finally, the negative predictive value, or NPV, which is a statement of the probability that someone who has tested negative really does not have the disease. And again, with sensitivity and specificity, we really do want both of these measures of the validity of the diagnostic tool to be as close to 100% or 1.0 as possible. Now, to help you with my example, looking at all four measures of validity for a diagnostic tool, I need to give you a quick reminder of probability that you will remember from your school days. Imagine we have a bag containing seven coloured marbles. In the bag, we have 4 red marbles, 2 blue marbles, and 1 yellow marble. Imagine we take a marble without looking at random from the bag. What is the probability that it is red? We put it back, mix them up, and repeat. Now what is the probability that we pick blue? And finally, after replacing and mixing, what is the probability of picking yellow? Now, if you want to play along, feel free here to pause the video to see if you can answer the 3 probabilities. Okay, the answers are: for red, we have 4 chances out of a possible 7 marbles to get red, so the probability is 4 out of 7, or simply 4 sevenths. Similarly, the probability is 2 sevenths for picking a blue, and finally 1 seventh for picking a yellow. Notice, as we have considered all possible colours in this example, all possible outcomes, these 3 answers all add up to 7 sevenths, i.e. 1, as it should be. Also, we are reminded that as well as using decimals or percentages for expressing probabilities, we can also use the language of fractions for dealing with probabilities, but I expect you already remembered that. If you got the answers correct, or at least agree with my explanations, then you are good to go with the next bit. So here's some pretend data for a diagnostic tool that screens for breast cancer. I give the web address where I borrowed these fictitious values at the bottom of this slide. Now, they might be fictitious, but they are broadly realistic for the type of data that is generated for the study of such a diagnostic tool. The first thing you notice is that out of the roughly 100,000 women tested, the overwhelming majority do not have breast cancer at the time of being screened. Just look here at the disease absent column. The total number of women with breast cancer here is less than 2% of all those tested, so a relatively small proportion as expected. Now, you'll also notice that typically with such tables, there can be vastly varying sizes of values, and that is absolutely fine and very, very common. So with these values, let's calculate all 4 measures of validity for this particular fictitious breast screening tool. First, the sensitivity, and recall this is the probability that someone with the disease will indeed test positive. So we need to focus on that first column of numbers, those where the disease is present. We calculate this probability by dividing the number of people who are true positive with the total number of women who truly have breast cancer. And with the help of a calculator, we get the answer 0.949, or just shy of 95%, which is nice and high as we want. Remember, we'd ideally want it to be 100%, but we might in real life have to live with such a high value as this instead. Okay, onto the specificity, which you will remember is the probability that someone without the disease will test negative, as they should in a perfect world. So in this case, we need to focus on the second column of numbers, i.e. the disease absent column. Now we calculate this probability by dividing the number of people who are true negatives with the total number of women who truly do not have the breast cancer. And calculate it out once more, and this comes out to be 0.969 or approximately 97%, which is even better. So far as the diagnostic tool of breast screening is concerned, we have values of 95% for the sensitivity and 97% for the specificity. So far, so good. Now let's consider the issue from the perspective of an individual woman who has been told either that she has breast cancer or that she has not got breast cancer. This is where the positive and negative predictive values come in. Starting with the negative predictive value, the NPV, remember that this is the probability that this person, having tested negative, really does not have the disease, which is the result any woman would want to hear, of course. For this measure of validity, we now focus on the bottom row of values, the testing negative values, and we divide the number of true negatives with the total number of women who tested negative. Okay, calculator out, and we find the reassuringly high value of 0.9992, i.e. very, very close to 100%. Okay, on to the final measure, the positive predictive value. So, imagine the woman receives the devastating news that she has tested positive. Her world feels like it's falling apart, but wait just a moment, and this part is really important. If you naively expect that her probability of really having breast cancer at this stage is the same as the sensitivity, i.e. 95%, then you would be mistaken. Recall, the positive predictive value, the PPV, is the probability that someone who has tested positive really does have the disease. And for this, we now focus on the top row of values, i.e. the testing positive counts, and we divide the number of true positives with the total number of women who tested positive. Calculate out one final time, and we get not 95% as you might have expected, but only 0.317, which is approximately 32%. This is startling at first sight, which is why I have included these last two measures of validity. On these fictitious values, if a woman was told that she had tested positive and the actual chance of her having breast cancer is still only 1 in 3. And this comes about because of the small but not tiny number of false positives when this test was put through its paces. And I'm hoping that even though this was a fictitious set of data, that it has at least illustrated the importance to you as a practicing nurse why you need to be aware of these extra measures of validity of diagnostic tools, because it will help you when you're talking to your patients. So, when we look at all 4 measures of validity for diagnostic tools side by side, we can see why the manufacturers like to quote the sensitivity and specificity, and these are overwhelmingly the values that are indeed quoted in research. However, should you make it your business as a nurse to find the relevant values for the PPV and NPV, so that if your job entails talking to patients post-screening, then you will then be able to tell them information that is relevant to them personally and not simply relevant to the machines manufacturers. And by the way, during the pandemic, and yes, I know it's still ongoing, I suspect significant values of false positives led to people unnecessarily having to self-isolate, but more importantly, the number of false negatives will have contributed to the spread of the virus being so hard to contain. Even if everyone had been compliant with self-testing, and ignoring for the moment our anti-vaxxer friends, anything less than 100% specificity or 100% NPV will have caused many people to be falsely reassured that they were okay to go into work. And curiously, for the COVID test we've all been using, I have been unable as yet to find accurate values for these 4 measures of validity. And I suspect in any case that they will vary quite a bit between manufacturers. So to end this bit, here is a useful summary slide using how all 4 measures of validity are calculated. Okay, statistics relating to diagnostics can be now put to bed, and the last bit of descriptive statistics that I want to cover in this video is regarding studying the risks of developing a disease or condition rather than looking at the probability of accurately detecting it. And again, I'm picking out those that appear most common in the literature and therefore in systematic reviews. The first 2 measures I want to cover, and I do see these in lots of systematic reviews, are the odds ratio and the risk ratio. The risk ratio, by the way, is also known as the relative risk. It's the same thing. Once again, we'll be dealing with a simple 2x2 table in the main, which you'll remember in the textbooks is sometimes called a contingency table. But instead of disease status, we now have disease outcome, because we are now interested in the risk factors associated with the onset of various diseases. And instead of test results, as we had for diagnostic tools, we now have exposure category, which in this simplest case is whether an exposure was present, e.g. smoking cigarettes, or absent, e.g. not smoking. Now we will use this same table of values to unpack what is meant by the odds ratio and the risk ratio. Let's start with the odds ratio. An odds ratio is used when you are carrying out a retrospective study known as a case control study. E.g., you might be taking a case history of people who already have the disease of interest. Of course, we would also need to take the case history of a control group of people who are similar in every other way, age, gender, socioeconomic status, for example, except that they do not have the disease. So a retrospective study is where you kind of look backwards in time from the present point. Now, I'm not going to motivate this formula simply because you only need to know how to interpret the values calculated. The 2 books I mentioned in the reference list by Ward et al. And by Peacock and Peacock can give you more information for those who are curious. But for the record, the odds ratio is calculated as given here. Crucially, it is no longer a value confined to being between 0 and 1, as was the case in the measure of validity in diagnostic tools, but can now be a value above 1 as well as equal to 1 or below. In fact, it can in principle have any value whatsoever. Now you might be slightly confused here because you might be thinking, but Phil, this is a fraction. Surely fractions lie between 0 and 1. But remember, fractions, and we saw these back at school, can be top heavy, what's known as improper fraction. So the language of fractions can be used to express values that's greater than 1 as well. Also, for the sharp-eyed amongst you, you'll have spotted this curious hat on the OR symbol. This is simply stat speak to mean that this calculated value is only an estimate using a given sample available of the population or true value. And by the way, it is because descriptive statistics tend to only produce estimates that we have a need in the first place for confidence intervals, and I'll come back to that later. Now, before I give a worked example, we need to understand how to interpret an odds ratio, and this is the important bit for you when you are reading research. If the odds ratio is 1 or close to 1, then this is equivalent to the null hypothesis being correct, that there is no difference in the risk of the disease between the 2 groups because the odds are the same in both groups. Now think back to when we looked at the mean. A null hypothesis would be where the difference in means 0. Here, because we're looking at a ratio, the null hypothesis, when the 2 values are the same, is not 0 because we're doing 1, the top divided by the other, so 1 divided by 1, which is why null hypothesis number is the number 1. If, on the other hand, the odds ratio is greater than 1, then the rate of outcome condition, the disease being present, is greater in patients who've been exposed to the risk factor, e.g. smoking, compared to those who have not been exposed to the risk factor, e.g. non-smokers, and this would indicate that there is an adverse association between, e.g. smoking and lung cancer. Finally, if the odds ratio is less than 1, then the rate of the outcome condition is less in patients who have been exposed to the risk factor. This might be the case, say, for daily exercise and the development of obesity, where you might expect a beneficial association between exercise and the reduced risk of becoming obese. So, as promised, let's consider an example to help us in this. And I'm taking data from a seminal paper from 1950, which was looking at the association between smoking and lung cancer by Doll and Hill. Note now this is real data. In this case, taken for 645 men who had lung cancer, compared with a matched control group of 649 men who did not have lung cancer. And the first thing that I noticed overall here is a reminder of how back in those days, the great majority of men, and women for that matter, smoked. In this sample of nearly 1,300 men, almost 98% of them were smokers. So, applying the given formula to the data, we get the value of the odds ratio at just over 14.04, which is way bigger than the null hypothesis value of 1. So from this data, therefore, Doll and Hill estimated that the rate of lung cancer was around 14 times greater in smokers compared to non-smokers. Now, what I haven't shown here yet is the confidence interval, because Doll and Hill didn't show this in their paper, but I have calculated this using SPSS. So here I expressed the confidence interval to just 1 decimal place. SPSS gives 3 decimal places, and I think it would make the whole thing look far too complicated. Now here's a few things I want to point out with this confidence interval. Firstly, notice that the null value of 1 is not included in the full range of plausible values. So we, or rather Doll and Hill, were correct in claiming statistical significance. Secondly, unlike the case when we consider the confidence interval for a mean, here the confidence interval is not arranged nice and symmetrically about the measured value. Or to put it another way, the measured value of 14.04 is not smack bang in the middle of the plausible range. And this is because the way confidence intervals are calculated for odds ratios and other risk measures is different to the measures for the method for the mean, but we still interpret them in a similar way. So with this range in mind, we can say that the population value, or true value if you like, for the odds ratio for the occurrence of lung cancer in smokers versus non-smokers suggests that the rate of lung cancer lies somewhere between 3 times greater to a whopping 59 times greater. So however you look at this, I think it tells at the very least not to smoke, or to give up if you do, and back in 1950 it gave strong numerical evidence to the fact that there was a strong association between smoking and the occurrence of lung cancer, which then drove further research, finally proving a causal link existed between smoking cigarettes and lung cancer, all of which may sound pretty obvious to modern ears, but it was far from a settled question back then. I've been very careful not to claim that this measure of odds ratio is not a proof of cause and effect. It is only a demonstration, an expression of association, and you must bear that in mind with all these measures of risk that I'm going to be talking about. Okay, next concept is the risk ratio, or as it is sometimes called, the relative risk. Now this is very similar to an odds ratio in terms of what it's exploring and in terms of interpretation, but now it is predominantly used when you have a prospective study, i.e. when you are moving forward in time with what is known as a cohort study. Now you choose your cohort, a group of volunteers participating in what you are going to monitor forward in time, who are now, both groups, all exposed to a given risk factor, e.g. they all live in an area where there's an open cast mining, for example, and then you follow them forwards in time. In other words, there is no grouping initially. The grouping of those who have the disease versus those who don't have the disease will only become apparent at the end of their research, at the end of their fixed time period. So they could be looking at some lung ailment that might be associated with the near presence of open cast mining, such as COPD, which of course will only appear in some of the cohort and certainly not in all of them. So we start with an identical looking contingency table as we had for the odds ratio. And again, without going into the theory behind it, here is the formula for calculating the risk ratio. Once again, we notice the hat, which means that this is the formula for the estimate of the population risk ratio, given that we have only access to a finite sample. And also notice that once again, we see it is in the form of a fraction or ratio, and this means once again that we can get values below 1 as well as above 1. And of course, if the value of the risk ratio comes out to be close to 1, then we have to accept the null hypothesis as being true, i.e. that there is no association between the exposure category and the disease outcome. So let's look at a real-life example of where the risk ratio was used. This is the publication from 2003, looking at the data as it then stood for looking at the risk associated with hormone replacement therapy, HIT, and the subsequent possible development of breast cancer in women. Again, as with the case control study, the researcher had finally two groups, those who had developed breast cancer and those who did not. Of the 500,000 women in the study at the time of this publication, mercifully only a tiny fraction, just below 0.9 of 1%, actually developed breast cancer. In this case, the value obtained is, like our example from Don and Hills, also above 1, which is important, but in this case not so large a value. We have to consider the confidence interval before we can draw any conclusions. But before we do, a reminder of how we will interpret the risk ratio, which is essentially the same as that for the odds ratio. If the risk ratio is 1 or is close to 1, then this is equivalent to the null hypothesis being correct, i.e. we would say there is no association between the exposure and the disease. If the risk ratio is greater than 1, then the exposure is a potential risk factor for the disease. And finally, if the risk ratio is less than 1, then the exposure is potentially protective for the disease. Once again, I had to run SPSS with these numbers as the paper did not include them in order to find the 95% confidence interval. And here they are. Here I've expressed the confidence interval to 2 decimal places. As we found in our smoking example, the null value of 1 is again not included in the range of plausible values, so we can claim statistical significance. Also, the risk ratio is above 1. As it is 1.85, this tells us that women who take HRT are around 1.8 times more likely to subsequently develop breast cancer compared to those who do not take HRT. If you look at the values of the confidence interval, remember this is a range of plausible values for the true population parameter. That very large sample size of nearly 500,000 meant that there is a very high precision of the range of values. We can therefore say that the value of the risk ratio is genuinely just shy of 2. Okay, this is the last bit, and if you stuck with me so far, I'm really impressed. The final measure I'm going to cover in this video is the hazard ratio. If we are looking at something called a time to event measure, such as the mortality due to cancer treatment delay, or say the time to conception after fertility treatment, then a useful measure is the hazard ratio. It is produced as an outcome of a statistical test known as a Cox regression and measures the strength of relationship between two variables. There is the independent variable, e.g. the delay time in cancer treatment, which is called in regression the predictor variable or explanatory variable. And then there is a outcome variable, e.g. the rate of mortality, which is often called the response variable or the outcome variable. So the hazard ratio gives a measure of the change in risk for an outcome, e.g. death, for a given change in what is known as this predictor variable, as this explanatory variable, I beg your pardon. Calculating the hazard ratio is beyond the level of this video, so let's just see how we will interpret the hazard ratio and then looked at an example from research. Again, this is reassuringly very similar to how we interpreted odds ratios and risk ratios. Let's imagine we are looking at mortality versus delay time in the cancer treatment. If the hazard ratio is 1 or close to 1, then this is equivalent to the null hypothesis being correct, i.e. there is no relationship between the two. Delays in cancer treatment in this case would have no effect on mortality. If, on the other hand, the hazard ratio is greater than 1, then this indicates an adverse relationship, i.e. an increase in the delay of cancer treatment would increase the mortality rate amongst patients. And finally, if the hazard ratio comes out to be less than 1, then this would indicate a protective relationship, e.g. an increase in the delay of cancer treatment would reduce the risk of mortality rate amongst patients. In my example I'm about to show, guess which one it's going to be. Okay, now this is an example taken from Hannah et al. 2020, who were looking at mortality due to cancer treatment delay. It is a systematic review and subsequent meta-analysis and was published in the British Medical Journal, BMJ. And unsurprisingly, we see that there is a relationship between the delay in treatment and mortality, and even less surprising is that across a range of cancer types, the hazard ratio is almost always above 1. And note, even 95% confidence interval in each case, apart from the final one, is above 1 also, indicating statistical significance, which tells us that this is indeed an adverse relationship. That final confidence interval for the non-small cell lung carcinoma, that is almost certainly due to a low sample size, because look how wide that confidence interval is. But hazard ratios are nothing to fear, as they are very similar in their interpretation to odds ratio and risk ratio. Well, that brings me to the end of this video. And to summarize, in these discussions, we have reminded ourselves of how data is communicated in research through charts and tables, and the sort of descriptive statistics that we are likely to come across, e.g. values such as the average and the spread. And we have considered the most common types used in each case. We have looked also at perhaps less familiar descriptive statistics, such as the common measures of validity, sensitivity and specificity and the like, used in evaluating diagnostic tools. And also we have looked at measures of risk associated with exposures such as smoking or HRT through the ideas of the odds ratio for case control studies or the risk ratio for cohort studies. We finally looked at hazard ratios, which go further and give an indication of the change in such risk, for example, resulting from a delay in time for treatment. In all cases, it was recognized that such descriptive statistics measurements alone was not enough. There needed to be an expression of precision, and this was where the idea of the confidence interval entered the picture. And the confidence interval also helped us, along with the p-value, to draw out conclusions as to whether the results were statistically significant, i.e. unlikely to be due to chance alone, or not. In other words, whether the null hypothesis could be rejected or had to be accepted. So I hope you found it of some use towards the skills you will need when understanding the research that will form the background to your own systematic review. And as usual, here are my references to accompany these slides. And of course, as promised, the further resources, i.e. the links to the videos that I mentioned at various points in the presentation. You will of course need to access the slides themselves to click on these links. And finally, my usual disclaimer regarding images borrowed for this presentation. Once again, thank you for your attention, and I will see you in the next video. Cheerio.